The architecture of human knowledge is undergoing a seismic structural shift. For centuries, the scientific method relied on human observation, manual experimentation, and the slow, methodical testing of isolated variables. A researcher would formulate a hypothesis, design an experiment, gather data, and spend months or years analyzing the results. But today, the sheer volume of data generated by modern instruments far exceeds the cognitive limits of the human mind. We are drowning in petabytes of raw information, from the microscopic dance of proteins to the faint, ancient light of distant galaxies. Artificial intelligence is emerging as the ultimate synthesizer, a transformative force fundamentally changing the pace and nature of how we understand the universe. Historically, human progress has been bottlenecked by our capacity to process information. The invention of the microscope and the telescope expanded our literal vision, but the analysis of what we saw remained a distinctly human and therefore limited endeavor. The advent of early computing accelerated our mathematical capabilities, allowing for complex simulations, yet these computers still required explicit human instruction for every step. They could only answer the specific questions we knew how to ask. Modern artificial intelligence represents a fundamental evolution in pattern recognition, breaking that historical bottleneck. Traditional supercomputers calculate based on rigid physics engines. Artificial intelligence infers based on probability and learned experience. By processing immense datasets, identifying complex patterns hidden within the noise, and independently generating hypotheses, AI algorithms are shifting the scientific paradigm from trial and error to predictive design. The machine is no longer just a calculator, it is an active participant in the scientific method. Consider the deeply complex realm of biology and drug discovery. While the initial breakthrough of AlphaFold in predicting 3D protein structures captured global attention, the technology's application extends far beyond that singular milestone. Machine learning models are now actively identifying potential drug candidates by mapping complex biochemical interactions at the atomic level. They analyze the intricate folds and binding sites of disease-causing proteins, predicting which synthetic molecules will successfully attach and neutralize the threat. They optimize molecular structures to enhance efficacy and reduce human toxicity long before a single physical experiment is conducted in a laboratory. This predictive capability drastically shrinks the timeline from laboratory concept to clinical trial. Pharmaceutical researchers use generative AI to construct entirely new molecular architectures, bypassing years of blind synthesis and dead-end testing. The result is a radically compressed pipeline for life-saving therapeutics, fundamentally altering the economics of healthcare innovation and offering rapid responses to emerging global pathogens. The echoes of those early biological breakthroughs still resonate, but the methodology has quickly migrated to other disciplines. In materials science, the quest for new compounds historically meant physically mixing elements and hoping for a serendipitous result. It was an arduous process that could take decades to yield a single viable commercial material, relying heavily on the intuition of veteran chemists. Now, deep learning algorithms sift through vast chemical databases, simulating millions of atomic combinations in a matter of hours. These advanced models predict and discover novel compounds with highly specific desired properties tailored for modern engineering challenges. Whether researchers are hunting for next-generation solid-state batteries to power electric vehicles or seeking room-temperature superconductors to eliminate energy grid loss, AI acts as an ultra-fast, intelligent sieve. It identifies the most promising candidates, leaving human scientists to synthesize and verify only the highly probable successes. This acceleration in materials science is the bottleneck breaker for green technology. The rapid discovery of highly efficient solar cell materials, lightweight aerospace composites, or novel carbon capture polymers directly dictates our ability to transition away from fossil fuels. AI is not just discovering new materials, it is accelerating the timeline for global energy independence and industrial sustainability. The implications of this accelerated discovery process extend directly to our broader fight against global warming. In the field of climate modeling, the sheer complexity of Earth's atmospheric and oceanic systems has traditionally overwhelmed even the most powerful supercomputers. Traditional physics-based models struggle to resolve small-scale phenomena like localized cloud formation, regional ocean eddies, or the complex interaction between soil moisture and air temperature, all of which drastically impact long-term climate change projections. Deep learning models are actively bridging this critical gap. By training on decades of historical weather data, ice core samples, and real-time satellite imagery, artificial intelligence enhances the accuracy of atmospheric simulations. These systems do not just crunch numbers, they learn the chaotic, non-linear dynamics of the Earth's climate system, finding correlations that traditional physics equations often miss due to the sheer computational cost of simulating every molecule of air. Because of this advanced pattern recognition, meteorologists can now forecast extreme weather events with unprecedented speed and precision. AI models can predict the rapid intensification of hurricanes, the exact path of a localized flash flood, or the onset of a prolonged drought days or even weeks in advance. This provides critical early warnings that save lives, protect agricultural yields, and allow municipal governments to allocate emergency resources with pinpoint accuracy. The long-term projections generated by these AI-assisted climate models offer a much clearer, high-fidelity picture of our planetary future. Policymakers and scientists can now simulate the cascading effects of temperature changes across complex ecosystems. They can model how a 2-degree rise in global temperatures will affect specific crop yields in the Midwest, or how melting ice sheets will alter coastal currents, turning abstract global data into actionable, localized mitigation strategies. Moving from the Earth's atmosphere to the depths of space, astrophysics is undergoing a similar data-driven renaissance. Modern telescopes and space observatories capture petabytes of data every single night, creating a massive observational backlog that human astronomers could never clear in a lifetime. Artificial intelligence is now the essential tool for making sense of the cosmos, acting as the tireless observer of the night sky, scanning the heavens while human researchers sleep. Neural networks are trained to analyze these massive datasets, filtering out the cosmic noise of the universe to find the faintest, most significant signals. They map the invisible scaffolding of dark matter by analyzing subtle gravitational lensing effects across thousands of galaxies simultaneously. This allows cosmologists to trace the fundamental structure of the universe, observing how galaxies cluster and evolve over billions of years, with a level of detail that was previously impossible to extract from raw imagery. This capability is particularly vital for exoplanet detection. When a distant planet passes in front of its host star, it creates a microscopic temporary dip in the star's brightness. AI algorithms analyze light curves from millions of stars simultaneously, identifying these subtle planetary transits far faster and more accurately than human analysis. They are discovering new, potentially habitable worlds hidden deep in archival data that traditional rigid algorithms missed entirely because the signal was obscured by stellar flares or instrument noise. Beyond finding planets, these systems are instrumental in detecting gravitational waves, the invisible ripples in space-time caused by colliding black holes and neutron stars. AI processes the complex interferometry data in real time, instantly alerting observatories around the world to point their optical instruments at the exact origin of the cosmic collision before the afterglow fades. This rapid response capability has birthed the era of multi-messenger astronomy, where we can both hear and see the most violent events in the universe simultaneously. Yet this heavy reliance on artificial intelligence introduces unprecedented challenges to the scientific method itself. The core tenet of science is reproducibility, and AI often functions as an impenetrable black box. When a deep learning model proposes a novel superconductor, predicts a complex protein fold, or identifies a new exoplanet candidate, it cannot always explain the mathematical reasoning behind its conclusion. It provides an answer without showing its work. This opacity forces the global scientific community to grapple with a profound epistemological shift. Researchers must develop entirely new frameworks to validate AI-generated hypotheses, ensuring that machine-derived discoveries are grounded in physical reality rather than algorithmic artifacts, training biases, or digital hallucinations. The focus of the human scientist is shifting from manually discovering the answer to rigorously verifying the machine's answer, a fundamental change in the daily practice of science. Despite these challenges, the democratization of these tools is actively reshaping who gets to participate in high-level research. Cloud-based AI platforms allow researchers at smaller universities or in developing nations to conduct complex simulations that previously required billion-dollar supercomputing facilities. Big data science is no longer the exclusive domain of elite, heavily funded laboratories, leveling the playing field for global innovation and bringing diverse perspectives to the world's most pressing scientific questions. As these systems become more autonomous, we are rapidly approaching the era of self-driving laboratories. AI will not only analyze the data, but actively formulate new hypotheses, design the experiments to test them, and control the robotic instruments that execute the physical tests. The cycle of discovery will run continuously, 24 hours a day, guided by an artificial intellect that never sleeps, never fatigues, and continuously refines its understanding of the physical world based on every new data point it collects. We are transitioning from human-led science assisted by computers to a symbiotic relationship where AI proposes and humans validate. AI's transformative role in accelerating scientific discovery is not about replacing the human scientist. It is about elevating human curiosity, removing the constraints of manual data processing, and providing us with a cognitive lens powerful enough to finally comprehend the staggering, beautiful complexity of the natural world.